Okay, boys and girls, okay?
That sounds good beyond that.
Okay, what we have here is a distillation apparatus, and I have simulated urine in this flask over here because you can actually separate all of the components of urine and the water and end up with pure water. So, this is how this thing works. Basically, we're separating a substance based on its boiling point, all right? Also by its solubility. If I had different liquids in there, it would be a different story. But what I have is a solute dissolved in a solvent. When I boil the solvent, what ends up happening is that the solvent vaporizes, leaving behind the solute. The solute in this case is not urine, it's potassium dichromate. So the water vaporizes up into this portion of the tube, it hits the thermometer head, showing about 101 Celsius, and then it moves into this portion of the tube. Now I don't have water available on this table, but normally a water input would be put into this area here, which circulates around an inner tube, cooling it off, and that's the water exit tube right there. Then what happens is once the vapor is cooled down, it runs down into this portion and then it drops into the receiving flask over here. As you can see, that potassium dichromate solution is coming over as an absolutely pure solution of water right there. Now, someone had a question back here. That's right, I remember the question now. Okay, the question is that if you had several liquids mixed together, what would happen? Let's say we had 3 liquids mixed together and we needed to separate the liquids. One boils at 39 Celsius, one boils at 68 Celsius, and the other is water boiling at 100 Celsius. If I started heating this up, the first lowest boiling point liquid would start to boil, and that would vaporize out, coming out over here and going into the receiving flask. I could monitor the temperature at 39 degrees, and then as soon as the temperature started to rise, I would know that the lowest boiling point liquid would be all the way over. I'd remove the receiving flask and collect that liquid, put it back, okay, and then let the next liquid boil over and at 68 degrees, and then when it started to rise, I would pull the receiving flask off and collect that liquid. And then finally you'd end up with pure water in that flask over there. Okay, now if you want to, you can actually do this a couple times and actually purify the liquid even more. They have a setup like this under vacuum. Now you guys haven't learned about this yet, but you can actually boil substances if you put everything under vacuum. And this is actually a setup where you can pull a vacuum right out of here, okay? And the vacuum basically will allow you to boil it without having to heat it. You can boil it at room temperature, okay? Do you have a question?
So if the water boils, like turns into a gas and it goes through the tube and condenses back to liquid on the other side?
Right, okay. It would be a lot more efficient if I had water, the water jacket filled with circulating liquid here. There's an inner tube in here that the actual continuous from the boiling flask into the receiving flask, and an outer jacket that you can circulate water around the inner tube. But I don't have a water hook up here and it wastes a lot of water. You just end up wasting water all day long. Are there any questions? Okay, yes, Isaac.
What function does that apparatus on top of the receiving?
This right here? Okay. Well, like I said, I had another tube that I should have inserted in between. I didn't have enough space, which is basically a vent tube. So you have to vent the system. At some point it's venting right there. Do you see it? Yeah. Okay, I mean if I wanted to, I could pull this off and I could vent it out the end here. Okay, as you can see it's coming right out. But I might as well vent it in that direction. So anyway, I should have put a vent here, and the vent is specially made so the liquid goes into the vent and then circulates and then drops back down again, just like it's doing there. But interestingly enough, if this was contaminated with potassium chromate at all, you'd be seeing some yellow in there, and you don't. It's perfectly clear. You could probably end up drinking that liquid right there. David?
What happens to, what's with the vents to the left of the, what is it,
This vent?
no, right, over the, which chamber is it called, the flask with the?
That's the receiving, that's the boiling flask and the
boiling
receiving flask.
The one over that, isn't it losing some water?
All right, you're talking about this?
No, the one
The one that-
The one that's, the one that has the thing.
Something like that.
It's coming
You're
out.
talking about here?
No.
Where?
The vent that's like.
Oh, it's losing lots of, this one here, where it's losing.
Yeah.
This one.
Yeah, wouldn't that be a?
Yeah, no, what I should have is that other piece inserted in between here, okay? And this one closed off. This should be completely closed off on that side.
Cause that, it makes.
See, I could probably take this off like this and put that right there. And you see it's coming out, the actual, well, that would probably be more efficient to do it that way. There we go. Okay. You can see it's coming up there. And in fact, if I were to put this in here, see how nicely all of this fits together? These are called standard taper glassware, and they're very expensive. This setup right here to go out by would be about $600 or $700. Anyway, this is only one of many different demonstrations and labs that we do here at SOCES. Thank you. Thank you.